Hello, students. Let me start with a question. Have you ever peeped through a door viewer, those tiny peepholes on doors? Or maybe you've seen someone wear spectacles for short sightedness? Guess what? Both of these everyday tools use concave lenses. Now, here's something interesting. Unlike convex lenses, which behave like moody artists, sometimes making big images, sometimes small, sometimes real, sometimes virtual, concave lenses are far more straightforward. They follow one simple rule every single time. No matter where you place the object, concave lenses always produce images that are virtual, erect, and diminished. In simple terms, the image is upright, smaller than the object, and you can't catch it on a screen. It's only visible when you look through the lens. Why does this happen? Well, it's because concave lenses don't bring rays together. Instead, they spread them out. The rays diverge after refraction, and if you trace them backward, they appear to come from a point called the focus on the same side of the lens. That's the secret behind their predictable behavior. And in real life, this property is super useful. Concave lenses are used in spectacles for myopia, helping people see distant objects more clearly by diverging incoming light before it reaches the eye. They're also used in door viewers, where they shrink the wide outside scene into a small, neat virtual image that fits into the tiny lens. So today, let's explore step by step why concave lenses always give these virtual, upright, and diminished images, and why this simple rule makes them such reliable helpers in our daily lives. Alright, let's take a step into the world of lenses again, but this time we are working with objects at infinity. Sounds dramatic, right? But all we are doing is looking at an object far, far away, like a star in the sky. So here's what happens. Parallel rays of light come from infinity and strike our concave lens. What's interesting is that after passing through the lens, they don't just converge on the other side like they would with a convex lens. Instead, they spread out, but here's the catch. They seem to come from the principal focus F on the same side as the object. Imagine the lens as a magician pulling a trick, making the rays appear to originate from the focus even though they've been spread out. Cool, right? And where does this lead us? We get a virtual image, which is erect and point-like, almost like a tiny spark in the distance. This image is formed at focus F, and it's so diminished that it's basically a tiny dot, like looking at a star through a telescope, small, far away, and looking like a point of light. Now, this is important. It's virtual, erect, and highly diminished. So, next time you're staring at the stars, think of that concave lens and how those rays would appear to spread out from a distant focus right back where they came from. Alright friends, let's play a little game. Imagine you're standing in front of a giant mirror at a fun house. No matter where you move, your reflection always looks a bit smaller and closer than reality. That's pretty much how a concave lens behaves. So here's the setup. We place an object anywhere between infinity and the lens. The light rays don't actually meet after refraction, instead they diverge. But if we extend them backward, they pretend to meet at a point somewhere between the optical center, O, and the focus, F. Sneaky, right? And what do we get in the end? A virtual image, always upright, always smaller. It's like the lens saying, sorry, I don't do real images. I only make mini versions by. Now the math lovers, here comes your treat. The lens formula is 1 by F equals 1 by V minus 1 by U. Just remember, for concave lenses, F is taken as negative. So, next time you try on someone's spectacles and everything looks tiny, don't panic. That's just the concave lens doing its job, making sure the world looks like a fun-sized version by. Hey there! Have you ever looked through a magnifying glass or wondered how a concave lens in spectacles works? Well, just like that, lenses can form images, but not all images behave the same way. Let's dive into the world of images formed by concave lenses, which share some pretty interesting characteristics. So, let's break this down. Image is always virtual. Imagine looking at yourself in a spoon. That reflection? You can't capture it on a screen, right? Same here. The image formed by concave lenses is always virtual. It's like a ghostly image, but you can still see it. Always erect. Ever notice how your reflection in a spoon looks like you, not upside down? Well, that's because concave lenses always form erect images, same orientation as the object. So, no surprises there. Always diminished, the image is always smaller than the object. Think of using a magnifying glass to look at tiny things like ants or coins. But with concave lenses, the image is just the opposite, it's always smaller. Located between focus F and optical center O, the image formed by concave lenses is always between the focus F and optical center O. So, keep these 2 points in mind whenever you're exploring how lenses work. Independent of the object's actual distance, no matter where you place the object, whether it's far or near, the image will follow the same rules. It's like a magic trick. The object's position doesn't change the characteristics of the image. Now, isn't that fascinating? Concave lenses are pretty special in how they form images, and understanding these key points is essential when diving into optics. Keep these points in mind as you continue to explore lenses and their magical properties. Hello students! Today, we are going to dive into a cool example involving a concave lens. It's like figuring out where your reflection is in a spoon. You know, the part where you look at yourself and it seems shrunk. Let's break it down step by step. Step 1. The formula. We start with the lens formula, which is a mathematical relationship between the object distance, u, the image distance, v, and the focal length, f. The formula is 1 by focal length equals 1 by image distance minus 1 by object distance. So mathematically, this is written as 1 by f equals 1 by v minus 1 by u. Now, let's plug in the values we know. Step 2. Substituting values. In our case, the focal length of the concave lens is minus 15 centimeters since concave lenses have negative focal lengths. The object is placed at minus 30 centimeters from the lens as we are considering the left side. So, substituting these into our formula, we get 1 by minus 15 centimeters equals 1 by v minus 1 by minus 30 centimeters. Step 3. Simplify. Now let's simplify the equation. We can rearrange it to make it look easier to solve. 1 by v equals 1 by minus 15 centimeters plus 1 by 30 centimeters. This is simply adding the fractions. Let's work through this. 1 by v equals minus 1 by 15 plus 1 by 30. Step 4. Solve. To solve this, let's find a common denominator. The common denominator between 15 and 30 is 30. So we rewrite it as 1 by v equals minus 2 by 30 plus 1 by 30. Now, combining the fractions, 1 by v equals minus 1 by 30. Step 5. Final answer. To find the image distance, we just take the reciprocal of both sides, v equals minus 30 centimeters. So, the image is located at minus 30 centimeters on the same side of the lens as the object. And there you have it. The image is virtual, erect, and diminished, just like the image you see in a spoon when you're holding it up close. It's a fun and real-world example of how concave lenses work. Keep in mind that concave lenses always produce such images, virtual, upright, and smaller. Alright students, let's wrap up our learning about concave lenses with a quick summary. Buckle up. When the object is at infinity, imagine looking at something super far away. What happens? The image forms right at the focus point, F. But here's the twist, it's virtual, erect, and diminished. So, no scary giant images here. The further away you go, the smaller and more normal the image becomes. Now, what if the object is closer at a finite distance? Picture something that's not super far, but still quite a distance. The image shifts between O, the optical center, and F, the focus, still virtual, erect, and diminished. No surprises there, it stays pretty small and upright. Fun fact, concave lenses never make real images. They're always creating images that you can't actually project onto a screen. Pretty tricky, right? Real life uses. How do we actually use concave lenses? Well, if you've ever worn spectacles for myopia, nearsightedness, used a peephole in a door, or looked through optical instruments like microscopes, you've been using concave lenses without even knowing it. They help us bring things into focus, making faraway stuff clear. And there you have it, the magic behind concave lenses. Now, go ahead and explain this to a friend. You've got it.